Hi everyone. So let's prove problem 16. So assume that the GCD between A and B is 1. Then we have the highest factor dividing A and B is 1. So in particular, there is no prime which divides both A and B. As we can factor, if there is a prime that divides A and B, then that means that the GCD of A and B would have to be bigger than that particular prime by definition. Then that's a direct way to show the forward implication. Then there is no prime P such that P divides A and P divides B. Because if there is such a prime, that would mean that it is less than or equal to the GCD of A and B, as it would be one of the factors of A and B. So let's go in the other direction. So consider the GCD of A and B. So we have D is the GCD between A and B by the prime factorization theorem. We can write D as a product of primes. So we must have one of the prime factors Pj dividing both A and B. But that's impossible. So that means that D must be equal to 1. So D is equal to 1. So let's move on to the next question. So question 17 says the following. If P is prime, and the GCD between A and B is equal to P, and then they're asking for the GCD between A squared and B squared. I claim that is equal to P squared. So, well, what we can write by the prime factorization theorem. We can write A and B as products of primes. And since P is one of the divisors of A and B, in particular the highest common divisor, so it must be in those prime factors of A and B. So you have P times the other prime factors of P, of A, which would be, let's just use Q. Q1, QS, and similarly B is equal to P W1 to W R. So that means, this gives you that A squared is P squared Q1 squared to QS squared and B squared as P squared W1 squared to WS squared. So we have that P squared divides both A squared and B squared. So in particular, it divides the GCD of A squared and B squared, which is equal to D. So notice here that we have also written the prime factorization. So remark is that we have written the prime factorization of A and B. From star. The prime factorization of A squared and B squared. So apply the prime factorization theorem again and write D as products of primes. So D is equal to, so as P squared is one of its factors, so you have P squared times P1 up to pk. But since D divides A squared and B squared, then by the prime factorization theorem, due to the uniqueness, we have that there exist, so by the prime factorization theorem, D as a factor of, the form wi or qj. So assume it is just qj. Assume it is qj. And consider T to be equal to P times Qj. First, we'll prove remark that A written as P times Q1 to Qs and B is equal to P W1 to WR. We can't have Qi being equal to Qj for any I and j. Wj for any I and j, as that would mean that P times that Qi would divide both A and B, and it is bigger than. It is strictly bigger than P, which is by assumption the highest common factor of A and B. So now, going back to our line of reasoning, we have, so going back to our line of reasoning, we have that T, which is P times Q and J, is a factor of B squared. So that means that P times Q and J divides W. P times W1, P squared times W1, all the way to WS squared. So what this tells us, that Qj divides P times W1 squared to WS squared. So Qj is equal to P, and if it is P, we're done, or Qj divides W1 squared to WS squared. So Qj is equal to P, or Qj is equal to Wi for some I, which if it's Qj, we are done. If Qj is equal to P, we are done. if Qj is equal to Wi, then what this tells us that this forms a contradiction, and the reason that it forms a contradiction is by our line of reasoning that we said we cannot have any of the prime factors of A and B being equal to each other than P. Then we get a contradiction. All right, everyone. Yeah, I didn't want to do a short proof. It's just like, to me, this is clear conceptually. So I thought that it would be nice to have this proof. All right, see you guys.